Hello, friends. Here is something that surprises most beginners. You spend months learning calculus before college CS, but once you start writing real programs, calculus barely shows up. What actually powers your code every single day is discrete math. It is behind the logic in your if statements, the efficiency ratings on your algorithms, the structure of your databases, and the circuits inside the processor running your program right now. In this video, we are going to walk through exactly what discrete math covers, why it was built for computing, and how each branch connects to something you will write or design as a developer. Let us start by understanding what the word discrete actually means. Alright, so what does discrete actually mean? In mathematics, discrete refers to values that are separate and countable. There are clear gaps between them. Think of whole numbers on a number line. You can jump from 3 to 4, but there is nothing you need to visit in between. Continuous math, like calculus, works the opposite way. It deals with smooth, unbroken curves where infinitely many values exist between any 2 points. Now think about a computer. At its foundation, everything is a bit. A bit is either 0 or 1. There is no 0.5, no in-between state. That means computers are naturally discrete machines, and discrete math is the branch of mathematics designed to reason about exactly these kinds of countable, distinct structures. That is why the two are such a natural fit. Next, let us look at the first and most fundamental branch, logic. Logic is where discrete math and programming overlap most visibly. Propositional logic studies statements that are either true or false, and the connectives that combine them. When you write an if statement in code with logical AND, you are applying exactly this. The truth table on screen shows how AND behaves. The whole expression is only true when both P and Q are true. Predicate logic extends this by adding variables and quantifiers. You can now say things like, for all x, if x is prime, then x is odd, or x equals 2. That is a classic provable statement. The on-screen note captures it exactly. Proofs are how computer scientists verify that an algorithm always produces the correct result, not just in the cases they tested. Up next, sets and functions, which are the backbone of data structures and databases. Now let us talk about sets, functions, and relations. A set is simply a collection of distinct objects. No duplicates, no guaranteed order. In programming, this maps directly to data structures like hash sets and lists, and to concepts like the domain of valid inputs for a function. A mathematical function takes every element from one set and maps it to exactly one element in another set. That is precisely what a programming function is supposed to do. Consistent input, consistent output. Relations formalize the idea of a connection between elements. A database table is a relation in the formal mathematical sense. Each row describes a pairing between entities, like a user and their role. When you write a database query, you are performing operations that have rigorous definitions in relational algebra, which is grounded in set theory. Coming up, graphs and combinatorics unlock algorithms and complexity analysis. Here is where things get really powerful. Graph theory models relationships between objects using nodes and edges. A social network is a graph. A city map is a graph. The dependency tree your package manager resolves before installing software is a graph. Algorithms like breadth-first search and Dijkstra's shortest path algorithm are built entirely on graph theory. Combinatorics is the mathematics of counting arrangements and selections. How many ways can you arrange n items? N factorial. How many ways can you choose k items from n? That is, C of n and k, which equals n factorial, divided by the quantity k factorial times n minus k factorial. This counting is exactly what you use when analyzing big O complexity. When you prove an algorithm visits n times n minus 1, divided by 2, distinct pairs, that is combinatorics in action. Next, let us put all 5 branches together in the final slide. Alright, let us bring it all together. Discrete math has 5 core branches, and each one unlocks a real area of computer science. Logic gives you the foundation for compilers, formal verification, and understanding what your Boolean expressions actually mean. Sets and functions formalize data structures and the behavior of the functions you write every day. Relations power databases and query languages. Graph theory is behind network routing, dependency resolution, and pathfinding algorithms. And combinatorics gives you the tools to analyze and prove algorithm complexity, and it underpins cryptography as well. If you are just starting out, begin with logic. Every other branch builds on it. Once you are comfortable with truth tables and proofs, sets and functions will feel natural. From there, graphs and combinatorics open up quickly. Thanks for watching, and we will see you in the next one.